Organoids are tiny, self-organized three-dimensional tissue cultures derived from stem cells. These innovative biological structures can mimic the complexity of actual organs at a microscale, offering a revolutionary approach to studying human biology and disease. Organoids can be developed to replicate various organ systems, including the brain, liver, intestine, and more, providing researchers with a powerful tool for investigating organ development, disease mechanisms, and the effects of drugs in a controlled, laboratory environment. The science behind organoids involves directing stem cells, cells with the potential to become any type of cell in the body, into developing into specific types of organ cells. By providing these cells with the right environment and chemical signals, they naturally begin to organize into complex structures that resemble miniature versions of organs. This process leverages the inherent ability of stem cells to self-organize and differentiate, embodying the structural and functional properties of the target organ. Organoid Intelligence, OI, is an emerging interdisciplinary field that sits at the crossroads of biology, computer science, and neuroscience. It involves the development and study of biological computing systems using three-dimensional cultures of human brain cells, or brain organoids, potentially interfaced with brain-machine technologies. The premise of OI is to utilize these lab-grown cerebral organoids as a form of biological hardware, aiming to create computing systems that could one day offer computational capabilities, surpassing those of traditional silicon-based computers, while being more energy efficient. The vision behind OI is grounded in the unique attributes of the human brain, such as its unparalleled capacity for parallel processing, learning, memory, and energy efficiency. By mimicking these properties, OI seeks to overcome the limitations of current computing architectures, especially in tasks that involve complex pattern recognition, decision-making, and adaptive learning. Current research in OI focuses on harnessing the organoids for basic computational tasks, understanding brain development, and exploring potential applications in treating neurological disorders. Key to OI's approach is the integration of organoids with electronic interfaces, allowing for the input and output of information. This is achieved through technologies like high-density multi-electrode arrays, which can stimulate the organoid and record its electrical activity. Early experiments have demonstrated the potential of organoids to perform tasks such as speech recognition and solving nonlinear equations through a process known as reservoir computing. This involves exploiting the dynamic responses of the organoid's neural networks to process information in a way that is fundamentally different from traditional computers. In summary, organoid intelligence represents a bold attempt to bridge the gap between biological systems and computational technology. It not only opens new avenues for understanding the human brain, but also heralds a future where computing could become more akin to the processes found in nature, potentially revolutionizing how we approach problems in AI, medicine, and beyond. However, it also brings forth complex ethical considerations, especially as research progresses towards more advanced capabilities, necessitating a careful examination of the implications of blending biological life with computational functions. Organoid Intelligence, OI, leverages the unique capabilities of brain organoids, miniaturized, simplified versions of the brain created from stem cells, to mimic the human brain's computational and cognitive functions. This cutting-edge approach offers several strengths that distinguish it from traditional computing paradigms, including silicon-based computing and artificial intelligence, AI, as we currently understand them. Here's an exploration of the core strengths of organoid intelligence: biological complexity and efficiency. One of the primary strengths of OI lies in its biological basis. Brain organoids can replicate some of the complex structures and functions of the human brain, including neural networks and synaptic connections. This biological complexity allows organoids to process information in ways that are fundamentally different from, and potentially more efficient than, silicon-based systems. The energy efficiency of biological systems is particularly notable, with the human brain capable of performing vast numbers of operations per second while consuming roughly the same amount of energy as a low-wattage light bulb. Parallel processing capabilities, The human brain excels at parallel processing, handling multiple tasks simultaneously through its extensive network of neurons and synapses. Organoid Intelligence seeks to harness this capability, offering the potential for computing systems that can efficiently manage complex, multifaceted problems in real time. This is in contrast to traditional computers, which often process tasks sequentially or require significant resources to simulate parallel processing. Learning and adaptability. Another significant strength of OI is its potential for learning and adaptability. Brain organoids, through neural plasticity, the ability of neural networks to change and adapt, could provide a basis for computing systems that learn from experience, adjust to new information, and improve their performance over time. This feature is particularly appealing for applications requiring autonomous decision-making and problem-solving in dynamic environments. Potential for neurological research and therapeutic applications. Beyond computing, OI offers powerful tools for studying the human brain and neurological disorders. By modeling brain diseases and disorders within organoids, researchers can gain insights into their underlying mechanisms and test potential treatments. This could lead to breakthroughs in understanding and treating conditions such as Alzheimer's disease, autism, and epilepsy. Sustainability and environmental considerations. In an era increasingly concerned with energy consumption and environmental impact, OI presents a more sustainable alternative to energy-intensive silicon-based computing. If organoid-based systems can indeed operate with significantly lower energy requirements, they could contribute to reducing the carbon footprint of data centers and computing infrastructures. Organoid Intelligence, OI, in space exploration and astrobiology. OI's biological complexity and energy efficiency offer unique advantages in space exploration and astrobiology. Unlike traditional, energy-intensive computational systems, OI-based technologies could operate with significantly lower power requirements, an essential factor in long-duration space missions where energy resources are limited. Organoids, particularly those mimicking human brain functions, could be used to process complex data onboard spacecraft, offering real-time analysis without the need for constant communication with Earth. This capability is vital for autonomous decision-making in deep space exploration, where communication delays pose challenges. In astrobiology, the study of life's potential in the universe, OI systems could simulate and study life processes under various extraterrestrial conditions. For instance, organoids could be used to understand how biological systems might adapt to environments found on Mars or Europa, providing insights into the search for extraterrestrial life. The inherent adaptability and learning capabilities of OI make it well-suited to model biological responses to extreme conditions, aiding in the design of life detection experiments on other planets. OI's role in robotics and autonomous systems. The strengths of OI, particularly its adaptability and complex pattern recognition, position it as a powerful foundation for advancing robotics and autonomous systems. Traditional robots often rely on pre-programmed responses and struggle with unpredictable environments. In contrast, OI-based systems could leverage the learning and adaptability inherent in biological organoids, allowing robots to better navigate and respond to changes in their surroundings. This capability is especially beneficial for creating more autonomous, flexible robots that can perform tasks in dynamic or hazardous environments without human intervention. For example, search and rescue robots equipped with OI could independently navigate debris fields, adapting their strategies in real time to locate survivors. How OI enhances neuromorphic computing and AI. Neuromorphic computing aims to mimic the neural structures and processing methods of the human brain to create more efficient and powerful computing systems. OI's detailed replication of brain functions at a cellular level provides a blueprint for developing neuromorphic systems that more accurately reflect the brain's architecture and processing capabilities. By studying how organoids process information, researchers can design AI algorithms and hardware that better emulate human cognitive functions such as learning, memory, and sensory processing. This could lead to AI systems with enhanced problem-solving abilities, lower energy consumption, and the capacity to learn from unstructured data, mirroring the human brain's flexibility and efficiency. The advantage of OI for BCIs, brain-computer interfaces, BCIs, create direct pathways between the brain and external devices, offering profound implications for medical rehabilitation, communication, and augmentation. OI's biological basis provides a more natural interface for BCIs, potentially leading to systems that integrate more seamlessly with the human nervous system. By utilizing organoids that replicate specific brain functions, OI-based BCIs could offer more precise control, higher fidelity in communication, and better adaptation to individual users. For individuals with paralysis or neurological conditions, this means BCIs that could more accurately translate thoughts into actions, offering improved independence and quality of life. The parallel processing and efficient energy use of OI also mean that such interfaces could operate continuously without significant power demands, essential for long-term, wearable BCI applications. How Organoid Intelligence enhances security and encryption. Organoid Intelligence, OI, brings a biological dimension to the field of cybersecurity and encryption, leveraging the complex and dynamic nature of brain organoids. Traditional encryption methods rely on mathematical algorithms that, while currently secure, could potentially be compromised by future advancements in quantum computing. OI offers a fundamentally different approach by potentially using the unique patterns of neural activity within organoids as the basis for generating encryption keys or for secure data transmission protocols. The inherent complexity and unpredictability of these biological processes provide a level of security that is difficult to replicate or predict with conventional or even quantum computing techniques. This biological randomness could enhance the security of encrypted messages, making unauthorized decryption exponentially more challenging without the specific organoid-generated key, thus offering a new paradigm in secure communications. In medical research and healthcare, the strengths of OI lie in its ability to replicate human organ systems at the microscale, including the brain, through organoids. This provides unprecedented models for studying diseases, testing drugs, and understanding complex physiological processes in a controlled, laboratory setting. For conditions like neurodegenerative diseases, brain organoids can model disease progression and response to treatments in ways that animal models or traditional cell cultures cannot, potentially accelerating the discovery of effective therapies. Moreover, the use of patient-derived stem cells to create organoids can pave the way for personalized medicine, allowing for the testing of treatments tailored to the individual's genetic makeup, thereby improving treatment outcomes and reducing adverse reactions. OI's biological basis ensures that these models more closely mimic the actual conditions within the human body, enhancing the reliability of research findings and their applicability to patient care. Advantages of organoid intelligence for drug discovery and testing. OI's potential to revolutionize drug discovery and testing stems from its capability to produce organoids that closely resemble human tissues and organ systems. This enables a more accurate prediction of how drugs will interact with human cells and organs before clinical trials, reducing the reliance on animal testing and simplifying the path from laboratory research to patient treatment. The efficiency and biological relevance of organoids could significantly shorten drug development timelines and increase the safety and efficacy of new therapeutics. By providing a human-on-a-chip model, OI allows for the simultaneous testing of drug effects on multiple organ systems, identifying potential side effects and interactions early in the development process, which is crucial for the design of safer drugs. Organoid intelligence in climate change and environmental monitoring. OI's ability to process complex data with high efficiency and low energy consumption makes it particularly suited for enhancing computational models used in climate change research and environmental monitoring. Traditional models require substantial computational resources and can still struggle to accurately simulate the intricate interactions within Earth's climate system. OI could contribute to more sophisticated and nuanced models, capable of integrating vast amounts of environmental data to predict climate trends, assess ecosystem health, and model the impact of human activities on the planet. Furthermore, OI's potential for developing biologically based sensors could advance environmental monitoring, offering sensitive, energy-efficient methods for detecting pollutants, monitoring biodiversity, and tracking changes in ecosystems in real time. By leveraging the unique strengths of OI, researchers can gain deeper insights into environmental processes and more accurately forecast future changes, supporting efforts to mitigate climate change and preserve natural ecosystems. How Organoid Intelligence contributes to personalized education and cognitive training. Organoid Intelligence, OI, stands to revolutionize personalized education and cognitive training by leveraging its biological underpinnings. Brain organoids can model the neural processes involved in learning and memory, providing insights into how different brains absorb and process information. This knowledge can inform the development of customized educational programs that adapt to the individual learning styles and needs of students, potentially making learning more efficient and effective. The strength of OI in this area lies in its ability to replicate human brain dynamics, allowing for the exploration of diverse neural pathways and how they contribute to cognitive functions. By understanding these mechanisms, educators could tailor cognitive training programs to enhance memory, problem-solving skills, and other cognitive functions, based on the specific neural profiles modeled by organoids. This approach not only promises to make education more adaptive and responsive, but also opens new avenues for supporting individuals with learning disabilities or brain injuries, offering strategies that are closely aligned with their unique neurological conditions. Organoid Intelligence's role in art and creative industries. The intersection of OI and the creative industries is a fascinating prospect, with Organoid Intelligence's strengths in pattern recognition and neural network dynamics offering new tools for creativity and art. OI's capacity to process complex data and generate patterns can inspire artists, musicians, and writers, providing a biological foundation for generating novel artistic concepts, compositions, and narratives. This biological approach to creativity is grounded in OI's ability to emulate the brain's natural processes, potentially leading to the creation of art that reflects the complexity and depth of human emotion and thought in ways that traditional AI cannot. For instance, organoids could be used to explore new forms of music that mimic the brain's response to sound, or to generate visual art that reflects the intricate patterns of neural activity. In this way, OI could become a collaborator in the creative process, offering perspectives that blend human intuition with the unique insights of biological intelligence, pushing the boundaries of conventional art and design. The ethical and philosophical implications of organoid intelligence. OI's emergence prompts a profound ethical and philosophical exploration regarding the nature of intelligence, consciousness, and the moral status of biological computing systems. The use of brain organoids in computing raises questions about sentience, personhood, and the rights of entities that possess biological brain functions. OI's strengths in mimicking human neural processes necessitate a careful examination of whether and how such systems might experience sensations or have interests that warrant ethical consideration. For example, if an organoid demonstrates learning or adaptive behaviors, does it imply a level of consciousness? And if so, what ethical obligations do we have towards it? These questions challenge existing ethical frameworks and invite a re-evaluation of our understanding of life and intelligence. Moreover, the potential of OI to model human cognitive processes brings up philosophical inquiries about the mind-body connection, the origins of consciousness, and the possibility of artificially replicating or enhancing human intelligence. It also raises concerns about privacy, autonomy, and the implications of using human-derived cells to power computational systems. As such, the development of OI not only heralds technological advancements, but also calls for a multidisciplinary dialogue involving ethicists, scientists, philosophers, and policymakers to navigate these complex issues responsibly. Organoid Intelligence, OI, is on the brink of revolutionizing fields from healthcare to computing, showcasing the immense potential of blending biology with technology. This innovative approach could lead to breakthroughs in treating diseases, advancing AI, and even reshaping environmental monitoring and the arts. As we explore the capabilities and ethical implications of OI, it's clear this technology could significantly impact our future for the better. For more insights into how OI and other emerging innovations are transforming our world and society, make sure to subscribe to my YouTube channel. Here, you'll find engaging content that delves into the latest in science and technology, offering a glimpse into the future of our world. Check out my videos for a deeper understanding of these groundbreaking developments. Subscribe now to stay at the forefront of scientific innovation and join the conversation on how new technologies are shaping our society.